Limits approaching infinity. Limits approaching infinity are commonly used to determine the horizontal asymptote of a function and to determine the long-term behavior of a sequence. And a few of these limits that are approaching infinity can be defined intuitively. So we know that 1 over n, as n approaches infinity, the limit of this will get closer and closer to 0. And we also know that 1 over n to the exponent r will also equal 0 as long as r is greater than 0. So these limits use sequence notation, but they're also true for the functions that they represent. So let's look at a couple of examples. So the limit of the function 2 over n plus 1 as n approaches infinity. So I could take a minute and plug in some terms. So like let's say if the first term, so n equals 1. So then I have 2 over 1 plus 1, so that's 1. Let's say if n equals 10, then I would have 2 over 10 plus 1, that's 2 over 11. If n equals 100, then I would have 2 over 100 plus 1, that's 2 and 101. So I can see that as n gets bigger and bigger and bigger, this value gets smaller and smaller and smaller. Eventually, it will reach 0, so the limit as n approaches infinity for the function 2 over n plus 1 is 0. Okay, let's try another example. So in this one, let's start with, let's just plug in some examples. So if n is 1, then I have 1 minus 3 over 1 plus 1. So that's negative 3 over 2. If n is 10, then I would have 100 minus 3 over 100 plus 1. So that's 97 over 101. If n equals 100, then I would have 10,000 minus 3 over 10,000 plus 1. And now I can start to see my pattern here. Oops, sorry. This is getting closer and closer to 1. So the limit as n approaches infinity of n squared minus 3 over n squared plus 1 is 1. Okay, and I can actually see that too because I can actually not consider these two terms here. And I can see that n squared over n squared is 1. So there's another way to solve this. Another strategy that might be useful later. So this is to divide each term by the variable with the highest exponent. Okay, so if we're going to do this, then we're going to take our n squared minus 3 and divide each of those by n squared, and n squared plus 1 and divide each of those by n squared. Okay, so what that's going to do, n squared divided by n squared, that's just 1. And 3 divided by infinity is going to turn into 0, just like we saw in the first example. N squared divided by n squared is 1. And 1 divided by infinity is also 0. So this is just another strategy to get the limit of 1. Okay, so either way. Let's try another example. Okay, we're going to look at this guy. So again, let's take a look at some terms. So if n is 1, then my answer is negative 2. This time I'm just going to go in order. If n is 2, then the function is 4. If n is 3, then I'm at negative 8. Sorry, I wrote that wrong up here. Let me fix this. Then I'm going to be at positive 16. And I can see that this These terms keep flipping back and forth between the positives and the negatives. And so in this case, there is no limit. Okay, I'm not getting closer and closer to a particular value. I'm actually getting further and further away. So this limit does not exist. Okay, let's look at this one. So I've got 2/3. When n is 1, I've got 2/3. When n is 2, I have 4/9. When n is 3, I have 8/27. When n is 4, I have 16/81. And I can see that this fraction keeps getting smaller and smaller and smaller towards 0. So the limit of this function is 0. Few homework problems for you to try, page 50, number 1 through 5.